Hello friends. So in the previous video we have just seen the maximum efficiency condition of the transformer with respect to changes in load current, right? Xi2 was varying, keeping power factor constant, and you found out the conclusion was that you get maximum efficiency with respect to the change in load current when the copper loss is equal to the iron loss, right? Copper loss is equal to the iron loss, or W x square WCU is equal to WI. This was the condition that we derived in the previous video. So now we can just write down the efficiency equation. So efficiency is equal to V2 into Xi2. You practice it writing in this formula. In some cases they might write this X outside, X V2 I2. That is also okay. But just if you put X and I2 together, you know that that is the load current. Okay. So this cos theta 2 divided by V2 into Xi2 into cos theta 2 plus Xi2 whole square, okay, into Re2 plus Wi. So this is the equation of the basic efficiency equation. So you can write it like this also: 1 plus 1 divided by 1 plus Xi2 square Re2 plus Wi divided by V2 into Xi2 into cos theta 2, right? You can write it. So in this video today we are going to see the maximum efficiency. Okay, when do you get maximum efficiency? By varying cos theta 2. And because you are varying cos theta 2 here, you keep Xi2 to be equal to constant. Okay, so this does not actually require any kind of derivation here, like what we did for change in load current. If you see this particular equation here, efficiency will be maximum clearly when this numerator term is minimum, right? So numerator term is minimum, okay, so this value will be minimum, and 1 divided by 1 plus minimum means the efficiency will be maximum, right? So when numerator is less, this term will be less, and when this term is less, you are getting higher efficiency, so maximum efficiency. So let us see what is this term. This term is nothing but losses divided by output power, right? Losses divided by output power. So in this expression, Xi2 is constant, right? In this particular section which we are discussing here, today's video, Xi2 is constant. So the only variable here is cos theta 2. Okay, so if this value has to be minimum, cos theta 2 has to be maximum, right? If this total value has to be minimum, naturally this denominator, this value here, I'll just write, if Xi2 square Re2 plus Wi divided by V2 Xi2 into cos theta 2 has to be minimum, okay, clearly cos theta 2 should be maximum. Cos theta 2 should be, because rest everything are constant, right? Xi2 is equal to a constant value, V2 is equal to constant. So the only variable here is cos theta 2. So now cos theta 2 is the load power factor. And how can power factor change? Power factor can change only from 0 to 1. Okay, that means when cos theta 2 is its maximum value, that is equal to 1, because power factor only changes from 0 to 1. When cos theta 2 is equal to 1, you get maximum efficiency for a particular Xi2, right? Xi2 is constant. You are keeping one load current value, some load current value. It can be half full load, 3/4 full load, anything. But what it is telling is that for any load current, you are fixing that you will get maximum efficiency when it is operating in cos theta 2 equal to 1. What is cos theta equal to 1? It is a UPF load, right? When cos theta 2 is equal to 1, it means that you are using a UPF load. Okay, so what it means is that you get maximum efficiency at a particular load current, okay, when the load matches to that of a resistive load. Okay, if your load, it could be an RL circuit, RLC circuit, etc., but the characteristics of that load should match that of a resistive load. Okay, the effective power factor should be UPF. That time you will get maximum efficiency for a particular load. So we can draw the efficiency curve once again. Okay, so this is going to be the efficiency curve. Okay, so Xi2 is equal to constant. For some Xi2 you are going to draw this efficiency. So in the variable is cos theta 2 and efficiency is here, efficiency, right? So at low power factors, you are going to have very low efficiency. Naturally, when you are having a highly inductive load or high capacitive load, the output power will be very less. Most of the power will be going as reactive power. Active power will be very less. That's why the efficiency of the transformer will be very low for highly reactive or highly capacitive load. So when cos theta is very low, efficiency is also low. And when cos theta 2 is equal to UPF, okay, cos theta 2 is equal to UPF, cos theta equal to 1, you will have maximum efficiency. So the graph will be looking like. So this is the point of maximum efficiency, or the value of maximum efficiency is this point. So this is efficiency maximum. Okay. So again you can draw this graph here, another graph, that is losses divided by output power. Losses divided by output power. Now in this case you are not going to have this concept of copper loss equal to iron loss, etc., because you are drawing it for one particular load current, right? One particular, and you are changing the power factor, keeping that load current at a constant value, right? So here what happens is that as the cos theta 2 increases, the efficiency of the transformer increases. So naturally the losses associated must decrease. Losses divided by output power should decrease, right? So losses we are not changing. Losses is a constant value here. So as cos theta 2 increases, the output power of the transformer increases, right? So we can put that here, right? So cos theta 2 increases, okay? So losses is constant, losses divided by output power, okay? When cos theta 2 increases, naturally output power is V2 x I2 cos theta 2. So losses by output power will increase. That means losses divided by output power will decrease. Okay, so this is the another graph. So initially output power is less, so it will be at a higher side, and as it goes down, it will come like this. Okay, and this will be minimum for a UPF load. So at this point, cos theta 2 is equal to UPF. This is the maximum efficiency point. Okay, this is the maximum efficiency point. Now we have understood that power factor also. So for any load current, if you want to have maximum efficiency of the transformer, you should operate the load at UPF condition. So that is another important point here. So now to consolidate everything, let us draw a graph, efficiency curve for variation of load current with different power factors, okay. So we will take just a reference power factor here initially. So here the variable is xi2, okay, and efficiency percentage is going to be in the y-axis. So this is at one particular power factor I am going to draw. So let us draw it, say this will be maximum efficiency at this particular power factor. So here x square WCU is equal to Wi, right? Iron loss is equal to copper loss. So let this be the power factor cos theta 2 is equal to say 0.8. Okay. So now if you increase the power factor, I have already told you the efficiency of the transformer will increase, right? So for this particular graph, what will happen is that, for example, I am varying the load current for another power factor, say 0.9. So what will happen is that this efficiency curve will just improve and it will become something like this. So transformer will have a higher efficiency. So this is cos theta 2 is equal to say 0.9, okay, and you will have the maximum point at cos theta 2 is equal to 1, okay, and from 0.8 if you decrease the power factor to 0.6, 0.5, 0.2, etc., the efficiency curve will come down like this. So this will be cos theta 2 is equal to say 0.2 or say 0.4, we will take it as 0.4, and this will be say for cos theta is equal to 0.2. Okay, so this is the variation of the efficiency curve with respect to load current for different power factors. So basically we have combined the two concepts in one graph. So in this graph, in this particular video, we have seen the variation of power factor, the variation efficiency curve, efficiency variation with respect to power factor. And I have told you for a particular load current, you will get maximum efficiency when your load is a resistive load. Okay, and when you are varying the load current, keeping power factor constant, you will get maximum efficiency when the copper loss is equal to the iron loss. So these are the two concepts that we have covered. With this, actually efficiency of the transformer concept is getting over. Theoretical concepts are getting over. Next, we will do a couple of videos on some numericals associated, which are quite important for certain competitive exam. So if you have liked this video again, so please like, share and subscribe this channel, and also please share these videos, because unless you share these videos, the vision of the channel to bring such videos to a larger audience for free will not be fulfilled. Okay, so I urge you to please share these videos, and also please do recommend these videos with your friends, because this channel has other videos also, like engineering circuit analysis, synchronous machines, DC machines, etc. So till I see you in the next video, it's me Varun signing off, and have a great day. Thank you.